Okay, well, hello again, everyone. So my talk is going to be an introduction to mutation testing. It's going to be a bit Android-oriented by the end, but for the most part, it can work on any language. First of all, let me introduce myself. I'm Xavier Gouchet. I'm working as an Android architect at Deezer. I'm also in charge of all the Jenkins and SonarQube administration. I also write the shell and Python scripts for all the developers. And I love bad puns, so if you have some, send them my way. As a matter of fact, it's also my birthday today. So I'm very excited to talk on my birthday, and so I decided to actually give a present instead of receiving. And so I've hidden Easter eggs in my presentation. And basically, what I ask you to do is to try and count how many Easter eggs you're going to see inside the presentation, and tweet them to me, and the first to tweet the correct number is going to receive a 3 months premium subscription to Deezer. And so you tweet me at xgouchet. Also, you can add the hashtag CODEMOBILE, hashtag get your code on. And that's it. So, first of all, let's have a show of hands. Who in here already uses unit tests? Very good. Integration tests, functional tests, test-driven development, good. Code coverage, mutation testing. Okay, you're in the right place. So, first of all, just the motto of why we use mutation testing is that when you write code, obviously you're going to have bugs. We all know that. And when you write tests, it's actually code. I mean, when you write tests in Android, you're actually writing JUnit classes. Therefore, your tests have bugs. Right. So we're going to start at the very beginning and come back to mutation testing. First of all, unit testing, you can see that as just getting an audition for a musician, and you just make sure that by himself the musician plays good music. Then you have integration testing. You get a couple, a duo, a quartet, several musicians, and you verify that they actually perform well together. And then you have functional testing. It's basically making sure that it's like a dress rehearsal. You know, all the whole orchestra and lights and the technique all works well. So you test your full production environment. Test-driven development would be basically just writing what you expect first and then actually do it. And in music, basically, it's just writing the music and then you perform it. And code coverage could be seen like this as Guitar Hero. Basically, you just count how much notes are covered by the musician. Just on a side note, this event was amazing. It's a band called Video Games Live, where they play with an orchestra music from a video game, and they had someone perform a Guitar Hero track on stage while the orchestra and the lead guitarist played the music, and it was amazing. End of the parenthesis. So basically you have your test, that's good, but the problem is that you're going to have bugs that are not covered by your test yet, and usually it's in the edge cases. Some user is going to have a weird phone or a weird configuration that's going to lead to a crash or just a bug report or just a 1-star review on the store. And we want to limit that. And code coverage in itself is not a good measure of your tests. Because basically, as you can see here, we have 100% code coverage, right? But the tests actually don't tell us anything, okay? One of the side effects of code coverage is that it can become, when a measure becomes a target, it ceases to be a good measure. Your code coverage just say how many lines of code have been visited during the test. But it doesn't give you any notion of is the line tested. It just says it's visited. Yeah, I've seen it. Yeah, sure. And so basically when you say, okay, I want to have a 80% code coverage or 100% code coverage, basically it's very easy to do. You just call your methods. You don't have to actually have an assert statement in your test to get your code coverage. And one of the side effects of Goodhart's law is Campbell's law is that the more a quantitative indicator is used for decision making, the more it's going to be corrupted. I've seen in some business, the management said, okay, we need code coverage because someone said to management that tests were good. Obviously they are. And they say, okay, we need to have 100% code coverage or the developer won't have their bonus at the end of the year. And so basically, yeah, you just call your code and you have the graph that goes up and shows, yeah, we have 100% code coverage, but we're not testing anything. So, always testing, let's take a look at what mutation testing is. Basically, the goals of tests when you're testing is to verify that the code works. It's the basic stuff. But it's also to make the contract explicit, especially if you are doing TDD. You just want to say, okay, I'm writing the test first because I'm writing the contract of what my feature, what my class is supposed to do. You're also guiding the development in WithTD because you're saying, okay, this is what my feature is supposed to do, and this is how someone else is going to interact with the code. It's also useful to prevent regressions, which may be caused by other developers or yourselves in the future. And then it also ensures retrocompatibility, so when you add a new feature somewhere else, it makes sure that you don't break something else on the other side of the app. And this last part is what we're interested in with mutation. Because basically we're going to, bad tests give you a full set of security and you're going to simulate bad code. You're going to simulate regressions, you're going to simulate mistakes added by other developers. Because basically you need to be as confident in the test you code as you are in the code you test. And that's me. So, mutation, basic idea, basic formula is write some tests, obviously. You mutate the code, you change the source code, not the test, but the source code. You watch the test fail and prove it, obviously. The first step, you write some tests. Okay, you have all your tests written, you got your code coverage, of course, and all the tests are green. Then you're going to change the code, and we're going to see later how we do that. But basically, you introduce some change in the code. And basically, if you change the code, it will change the behavior of the code, so obviously your test should fail. And so you run the test again, and you watch the test fail. And if the test fail, you catch the mutation, you code the mutation, and that's good. But sometimes the test doesn't fail. And so in this case, if the mutation survives, well, who knows? We got to dig deeper. So why would a mutation die? Well, a mutation can die because basically the change introduced changes the test condition. So basically you change the return statement, and so obviously you don't meet your assertions. You can have some unexpected exceptions. So the change will lead to a null pointer exception, or it's going to lead to a number format exception, stuff like that. You can lead to non-viable code. Although most of the framework tend not to do that, it could happen that the code that's changed cannot be compiled or cannot be executed. You're going to have some system errors because your change is going to send an out of memory or a Stack Overflow. And you can have, of course, timeouts because the change is going to lead to concurrency issues. Why would a mutation survive? This is actually a better question because it can be because the code is not covered by test. So basically, if it's not covered and you change it, you won't detect it. So we're back to the code coverage issue. It could be also a silent mutation. Silent mutation, I've had only a couple of those. It's usually when the mutation, the change you introduce, doesn't actually change the output, but it's normal. To give you a concrete example, I had a test. I had a function that would compute some, perform some mathematical operation on integers. And basically, there was one line where I added a and b. So I had c equals a plus b, and below, a few lines below, derived from this addition, I also add a modulo operation. And basically, the mutation changed the a plus b into a minus b, but because b was a multiple of my modulo, the result was the same. And so basically, I scratched my head first, but I dug into the code and I understood why it happened, and actually it helped me improve my algorithm for better performance. And then the most obvious reason for why a mutation would survive is that you can have an incomplete or a bad test suite. So we're going to give some example. First example, very, very simple, trivial. You have this function that says, okay, I'm adding two numbers, a plus b. Okay, fairly simple. And you have a test, a very bad test in this case. You have the test that says, okay, I'm asserting that when I add 5 and 3, the result is positive. And it's not that good a test, and I don't know if anyone will actually write that, but we're going to see that. So the test is green, of course. And then mutation is going to change a plus b into a minus b. And the test is still valid because 5 minus 3 is 2, which is obviously greater than 0. So changing I actually didn't change that, but if you actually use an assert equals add 5, 3, and 8, then you're going to make sure that your tests are catching the mutation. Second example, here we have some Boolean tests. So if we have both A and B set to true, we return 42. And otherwise, we just return 0. And the test, basically, it checks that when you call check with true and true, it returns 42. When you call check with false and false, it returns 0. And the test passed, of course. But then the mutation framework is going to change the AND to an OR operation. And the test is still green, because obviously we're missing a couple of cases. So adding those two cases in our test is going to make sure that we are going to catch the mutation. One case of mutation not leading, a mutation not being caught by test is, for example, something like that. You have a counter I that you're going to increment during a loop. So it's a very weird way to do a for loop, but basically you can increment it. And when you get to 100, you stop the while loop. And basically, the mutation could change the equals to a greater or equal, and it's still going to pass the test, because the change doesn't really change, in this context, the logic of your methods. So then, we're going to take a look at different mutation that we can have. So this is specific to the mutation framework that I'm using, which is called Ptest, but it's fairly similar in many languages. So basically, all the math operations are going to be switched. So plus becomes minus, and vice versa. The multiplication becomes division. The bitwise operations are shifted. Modulo becomes multiply. Power becomes AND, and the shifts are reversed. Also, for the conditions, inequalities or boundaries are changed. So basically, a greater than or equal becomes just a strict greater, and so likewise for the less or equal. The equals becomes not equal. Inline constants, so inside your code, if you have an int, byte, or short or long, if it's 1, it becomes 0. If it's max value, it becomes min value. And if it's n, any other number, it just becomes n plus 1. For float and double, it's just basically if it's 1, it becomes 2, otherwise it becomes 1. Then the return value are changed, so basically we change the mutation framework is going to change what you're returning. You can remove call to non-void to void methods, so basically the method is not called anymore. Will that have some impact? You can also remove call from non-void methods and return null instead. You can force if conditions to true or false. You can also have some various other stuff, basically. So when, for instance, when you have minus x somewhere in the code, it becomes just plus x. Increment becomes decrement. If you have a method that takes an argument of a type t and the return type is the same, it actually returns the argument unmodified. And new instances can be changed to null. And so let's get our hands dirty. So first of all, just to look at how you can add this to your Android Gradle script. Basically, you just add a plugin, and you can you apply the plugin. Just basic configuration. You need to give it to say which class you want to mutate. So it's your source code and not the test that's going to be mutated. So you can just give your root package name, or you can pinpoint to a specific package or even a specific class if you want. And basically, as a result, it's going to look familiar for those of you who use code coverage. It's basically an HTML page with your code, and highlighted are going to be the lines that are to be fixed. For instance, in this case, this line is actually not when the boundaries of the inequality operator are changed. So greater than becomes greater or equal. The test doesn't see the change. So let's do a little bit of test. So I've got this. Too big. I've got the Android architecture sample from Google, and I can run the test, and the test run, and basically all the tests are green. Just gonna make sure that it works. So first step, you make sure that your tests are green and everything's good. And then you can call actually a task that's called Ptest, Ptest. And it's going to build your application. It's going to find classes to mutate. And it's going to introduce mutation. So here we see that it created 88 mutation in the whole source code of the application. And then it's going to run the test again and see if the mutations were detected. So it takes a little while. But it's going to end soon. And basically, it gives a report. So you have some report in the console, but you obviously also have an HTML report. And those reports, it's just a coverage report, so you can see for each file the code coverage and the mutation coverage. So obviously, when a line is not covered, it's also it won't be detected when a mutation is in it. But for instance, if you go to this class, for instance, so we have a pretty good code coverage, but we have still some mutation that's outlived the test. And for this is the first one. So basically, if you remove the call to this method, you don't call this method anymore, the tests survive, which is obviously bad. And so basically, if you just add a single verify in your test. So save. You run the test again. So it's going to run it again. And it's going to try to see if the mutation is killed, is detected by your test. And finger crossed, but it should be. So just 30 seconds. And basically, when you look at mutation testing, the way to look at it is like, if you think that your test is your, it's the police of your code, you know, so it's there to catch the bad guys, the bugs. Then mutation testing, it's basically just a drill to see if your safety nets actually work. It's not going to help you find the bugs, but it's going to say, okay, I know that if I introduce a fake bug, the tests are going to see it. So if we look at the new code coverage and we use the same class, we see that now the same line has been caught. The mutation on this line has been caught by our tests. So let's go back. So now just a few things about this framework. First of all, yes, it does work with Kotlin because basically it works by changing the bytecode. So because Kotlin ends up in bytecode, it works. Actually, in the sample, I did create a small Kotlin class called calc with very basic tests. So I have 100% code coverage, but you can see that all my tests are bad. But so it does work, and it's able to understand to highlight the Kotlin source code. So it works in Kotlin. It probably also works in other JVM languages. So if you use Scala or Jython or anything else, JRuby, it will work with it too, maybe, because I didn't test this myself. It's highly configurable. Basically, you can say, okay, I only want 4 mutation per class or 10 mutation per class. You can say, I only want to mutate this class. You can also extend it, so you can write your own mutation engine. So you can have your own way of changing your code. If you think of some mutations that are pertinent for your code, your own code or business logic. You can also extend it to have mutation filters, to have different outputs than HTML or XML. Things that you should keep in mind is that, so that's what I just said, mutants won't find bugs in the code. They are just going to really reveal the issues that are in your tests. So it's really just a drill for your test. It's not finding the bugs, it's improving your tests in order to find the bugs. It's not bulletproof. So basically, when a mutation survives, it doesn't mean that your tests are bulletproof and that they're going to catch everything. It just means that you have a tighter safety net. But you could still have bugs arising with 100% mutation coverage. Because it's not bulletproof, it's not a viable metric. Of course, the better coverage, the higher coverage you get, the better. But it's not a viable metric, so it should not be used as a target or as a KPI for your bonus or something like that. And one thing also is that it only simulates atomic faults. So it's only going to change, a plus into a minus, or a return something into a return null, stuff like that. So the changes that it can introduce by default are just atomic changes. It cannot simulate, for instance, refactoring your sort algorithm for something else. So yeah, the scope of the changes are still quite small. And finally, it's a bit costly. In this example, so we have like I think 50 classes in this project, and we have 88 mutations that have been introduced. Creating the mutations and running the tests against them is costly. And so you shouldn't do that on your whole code base, of course, because if you have a large application, it can take a really, really long time. So personal recommendations about that is to only use it locally during your TDD process. Basically what I do when I have to write a new feature or to maintain an existing feature is that I'm going to work TDD usually and do what I do. Do my changes or create my new classes or whatever. And at the end, when I'm satisfied with the code, I'm done refactoring, I'm satisfied with the tests, I'm going to run a mutation testing pass just to check if I didn't miss any edge case. And usually, I get a couple of corner cases that I missed or things that are not tested. You can automatically trigger it in a pre-commit hook. So basically, you just have to create a script to know which classes were changed in the commit and in the configuration say, okay, I just want to run the mutation on those classes that were changed. I might share a gist because I have a script like that, but it's not, it's dirty, so I just clean it and then I might share it. We don't run it on our CI server yet because it takes a lot of time and we have a lot of tests. And so basically if you want to run it on your CI server, you have to run first your tests, and then you're going to run again your test with the mutation. So you basically double the time of your job, and you're also adding the time to create the mutations and run it against the test. So it's you can do that in a nightly build, but you can't do that on every commit. And yeah, coverage value should not be shared with management because if it's shared and if it becomes a target, it's fairly easy to tweak it and cheat. So your toolbox. So as I said, the mutation framework I'm using is called Ptest. It's a Java framework initially, so they already have a Gradle, Maven, and whatever script to run it against any Java project. There's also an IntelliJ Android Studio plugin that's called Zester, which basically allows you to run a mutation pass on a single class. So basically, just like you have, the test button in the margin of your source code, you can have also when you can run unit test or debug unit test, you're going to have also run mutation tests. And this is the plugin that I'm using, which is usable from the command line, and you can configure it to only run some tests. Also for the iOS developers in here, I found that this GitHub project which adds mutation testing for Objective-C. I didn't find one on Swift, but doesn't mean it doesn't exist. And mutation testing framework also exists in many languages. I know there is one for JS, Python, PHP. So if you're working in other languages and have unit tests there, you can add mutation testing. So that's me. Thanks a lot, everyone, for your attention. And if you have any question, please shoot away.